Hey, AP Chem. Today we're going to be talking about the Spec 20. So the Spec 20 is a piece of equipment that we can use, and it helps us use a technique called spectrophotometry. Spec 20, spec, the part there, comes from the spectrophotometer. You will also hear this called a colorimeter once in a while, and they kind of do the same thing, but we specifically are going to be using the Spec 20 or spectrophotometry. And what we're going to be using it for is to find the concentration of an unknown solution. And it's a technique that's used kind of in a lot of different industries that aren't just chemistry. So you use it in water quality. You use it in analyzing soil samples for specific ions. It can be used in a ton of different ways. And I would argue that it's one of the more important techniques that you learn within this class. So some of you may have used the Spec 20 already. Some of you haven't. The Spec 20 is kind of this beige looking box. It's about 18 inches to 2 feet wide. It's about a foot deep, and it has a couple of different components on it as far as its parts. And what happens is you got a little power light here. You turn that on. You warm up your machine for about 15 minutes before you get started with your experiment. And when you turn the machine on, that's when you kind of take time to, recombobulate yourself with the machine. And what you'll see on there is a display. The display, which I'll give you a better picture of in just a minute, has a little needle on it. And then it can give you two readings. It can give you an absorbance reading and it can give you a transmittance reading. There is also a sample compartment, and in the sample compartment, you will take your individual sample that you are testing and you will put it into a little container called a cuvette. So the cuvette typically is about 1 centimeter in length. It looks like a test tube, but it's designed to be kind of a little bit more technical. It's got a line printed on it. And then you also have this wavelength selector over here. Now, the wavelength selector works to adjust the type of light that you are going to be shooting at your sample. So we've talked in our previous discussions about the different types of wavelengths you see for the different types of colored light. And in this case, you can adjust the little knob to adjust the wavelength. And then there's a power control switch down here and the 0, and then the absorbance control here. And I'll tell you what those mean in just a second. So this is a picture of our sample compartment. Like I said, you get a little tube called a cuvette, and then the cuvette sits in this holder here. You do not want to dump the liquid in there. One year I had a student try to pour the liquid into there. No. So you take this cuvette, which is a little test tube, and you slide it in, and you have the line on the tube match up with the line on the cuvette holder, and then you close the lid, and that's how your sample goes in there. So that's generally how that works. So the internal kind of guts of your Spec 20, what happens is that there is a light source, and then the light source is next to a lens, which allows you to kind of focus the beam of light. So it's not just this diffuse light that you have, it's a focus beam. And then you send that focus beam into a prism. And a prism, kind of like a rain droplet, will split your white light that's sent to it into its rainbow components. So red, orange, yellow, green, blue, purple. And what you are able to do is when you adjust your wavelength, you are able to pick which wavelength of light you want and which color of light you're going to shoot at your sample. So then you have your little sample cuvette here. You shoot a full light beam to the sample. And then when you set up your experiment, you pick the wavelength so that this sample absorbs the maximum amount of light possible. And we'll talk about how you pick that later. And in theory, some of the light, if there are particles here that can pick up the light here and absorb it, that light's going to be absorbed and not as much is going to come out on the other side. And you are going to get a reading on your Spec 20 of either a percentage for percent transmittance or an absorbance value. And I'll talk about both of those in a minute. One of the things you need to know is that when you put a sample into a Spec 20, it has to be a colored sample. So when we talk about sending a light beam out into a sample, if you send a colored light beam, for it to be absorbed, there has to be a particle in solution that also has a color as well. So if I'm going to put a solution of sodium chloride into that cuvette, I'm not going to get a result because that has no color. So usually things that we look at them have some sort of rainbow color to them, whether they're red, orange, yellow, green, blue, or purple. And then we pick an appropriate wavelength for that. Okay, so this is a picture of the dial and the needle with your readings here. And in our case, we typically take a look at the top here, which is the percent transmittance. So percent transmittance is calculated by taking the intensity of the original beam and looking at the transmitted light that gets through and dividing the two. So we put our transmitted amount on the top, the amount we originally put in the bottom part of our division, and then we multiply that by 100%. So if we have a 70% transmittance, that means that we're going to have 70% of the light getting through from start to finish. So if I have a high transmittance, what that means is I have a lot of light going through my sample. And if I have a low transmittance, it means I don't have a lot of light going through my sample. And the way it works is that the more kind of colored particles you have in your cuvette sample, the harder it's going to be for that light to transfer through. So when we talk about those different concentrations of solutions, if you have a higher molarity solution, it should have a lower percent transmittance. Okay, so the whole point of this is eventually to figure out what is the molarity of an unknown sample. And so what we have to do is we have to set up our experiment to support finding that information. And the first thing you need to do is you need to set up an experiment with the correct wavelength. So the correct wavelength that you are going to pick for your experiment is going to be a complementary color to your solution color. So for instance, if I have, let's say, a red colored solution, I am going to want to pick a wavelength that is green. Complementary colors are across from each other on the color wheel. So if I have a red solution, I'm going to pick a green light. If I have a violet solution, I want to pick a yellow light to bombard at my sample. And so what you do is on the little dial on the machine, there are these numbers here located anywhere generally from about 400 to I think it's like 800 nanometers, and you can just turn the dial to a specific wavelength. And then actually what you do is you would take a sample of the solution you're testing and you would put it into a compartment at a specific wavelength. Then you record that wavelength. Excuse me. Then you adjust your wavelength a few more nanometers and you put the sample in. Adjust the wavelength, put the sample in, adjust the wavelength, put the sample in. And you do this across the entire spectrum of your different potential wavelengths. And what you are looking for is one of two things. You are looking for the best wavelength to show you the maximum amount absorbed or the lowest amount transmitted. So we talked about transmittance back here. The best wavelength is going to allow the least amount of light through here. Absorbance is kind of the opposite of transmittance. So if you think about transmittance as how much light can get through, absorbance reflects how much light is trapped inside this particular solution. So what they'll do is they'll make one of two graphs. They will either graph it where it's wavelength versus transmittance or wavelength versus absorbance. And what you're looking for is you're looking for on the absorbance graph a maximum amount of absorbance. So in this case, if we look here, this max shows up at about 450 nanometers. So I'm going to want to use 450 nanometers for my experiment. If there were a transmittance graph produced, it would basically be this graph flipped upside down. When you are comparing a transmittance graph, you are looking for the lowest amount of transmittance to pick the ideal wavelength. Then you set your experiment to that wavelength and then you carry on. Absorbance is calculated by taking the negative log of that percent transmittance and dividing it by 100. So if I get 70% transmittance, I would say absorbance is equal to the negative log of 70 over 100, okay? Absorbances should be under 1 as we are going through them, and they are a unitless number, whereas percent transmittance is a percentage. So what does this all have to do with finding the molarity of an unknown solution? There is a law called the Beer-Lambert law, or more affectionately known as Beer's law. And Beer's law states that A equals epsilon times B times C. And you're like, super, that means nothing to me. And now there's Greek. So here's what it is. A stands for your absorbance. So the absorbance value, or how much light gets trapped in your tube, is equal to this epsilon, which is the molar absorptivity constant. And it's the sensitivity of your particular chemical's ability to absorb that solution, times the path length, or the length of your cuvette through your machine. And for most of our cuvettes, it's going to be 1 centimeter, so it's kind of a non-factor mathematically. And what's most important is that it's equal to this C value. And C is not the speed of light in this case, it is the concentration of your solution. So what happens is, if you take a look at your absorbance, it is equal to this proportionality constant, E, epsilon, and the path length and the concentration. And so what that means is that if I can compare my absorbance, I can be able to figure out my concentration, or vice versa. So with this equation, and what we're going to be using is something called a calibration curve, you can figure out an unknown concentration of something if you have the absorptivity constant, the path length, and the absorbance value. So what does this look like in a lab? In the lab that we're going to be doing, what you need to do is you need to create a graph. And you are going to create a graph of several solutions that you confidently know the molarity of. So what we usually call those are calibration curves that we're making, and they are a set of standard solutions. So they're solutions that you personally made that you know the molarity of. And what we're going to do is we're going to measure those known solutions and their percent transmittance. Then we're going to turn their percent transmittance into absorbance and make a graph. That graph looks like this. You're going to put your concentrations on your x-axis because that's our independent variable, and then the absorbance depends on the concentration. So our standards are going to be a series of molarities that we know. And if we create a graph of that, you should get a straight line. And you're going to get an equation for that line, y equals mx plus b, if we use the slope equation that's probably given in our calculating program, okay? This constant, or this equation, y equals mx plus b, is what we're going to use to find any unknown concentration. Because what happens is the molar absorptivity constant is going to be the slope of this curve here. And assuming we have a 1 centimeter path length, everything should work out fine. Our absorbance value is going to be our y, and our concentration is going to be our x. So once we make this calibration curve, what we're going to do is we're going to take our solution that we don't know the concentration of, and we're going to put it into the machine. We are going to take a measurement of it, putting it into the machine, and then we're going to get that transmittance. We will convert the transmittance to absorbance, and then, and here's the cool part, you can put the absorbance into the y and solve for x, and you can get the concentration of the unknown. If you wanted to, you could also use this equation once you get the slope. So if I know that my slope is the molar absorptivity constant and my path length is 1, if I know my absorbance, I can use algebra to find my concentration. Both of them are legitimate ways to do that. So what we can do is we can use the absorbance values found through the Spec 20 to give us this calibration curve and figure out our molar absorptivity constant. And then in theory, the unknown is going to land probably somewhere between these standard values here, somewhere on this line for sure. And then we're going to be able to figure out the concentration of that unknown solution. Okay, so there are some questions for you about how to kind of interpret this graph, talk about picking an ideal wavelength and things like that I want you to give a try. If you have any questions, please come to a meet and we'll get things cleared up. Good luck.